I closed out that last video without closely looking at this particular question, so I want to revisit it real quick before we move on to the rational functions. So much like we were asked to do in our Unit 5 exam, you're given a polynomial function and you need to make a sketch of the graph, which in and of itself isn't all that challenging, but what I wanted to remind you of was this component here, the remainder theorem, how it's used to calculate f of 3. And with the remainder theorem, what that states is that the remainder when dividing by 3, x minus 3, the factor associated with this number 3, the end result will be the remainder following synthetic division. So rather than trying to substitute the number 3 in place of x in this function, we could literally just use synthetic division and find the number in the bottom right-hand corner when we're all finished. What we have to be extremely careful of here, however, is when setting up our synthetic division, it better look like this: 1, 0, negative 11, 18, and negative 8. It's got to have the extra 0 here because I don't know if you noticed it or not, but there was a missing term in this polynomial. There was no x cubed value. So we better include that, and when we place the 3 on the outside and work through the process, then the result that we get down here at the very end, this number in this position, is the remainder, and it is the result for f evaluated at 3. Now the second part of this question is equally interesting, I think. Use synthetic division to show that x equals 1 is a double root of this function, or in other words, that there's multiplicity there. And so again, if we set up synthetic division, we have to use 1, 0, negative 11, 18, and negative 8. And we're going to test the number 1 to see if it indeed is a factor, or I should say a solution that produces a factor. So the synthetic division process requires us to bring down this number 1, or to start with a 0 here. When those two are stacked, we add together. We multiply the numbers on the exterior, so 1 times 1 is 1. Add these together, multiply, add these together, multiply, add those together and multiply. Oops, and I did my math incorrectly here. 18 plus negative 10 is positive 8. So this is positive 8. And now we've got a remainder of 0. Normally we would test for other factors at this point, but we've been given a hint that there's a double factor at 1, so I'm going to use the number 1 again. If I continue the synthetic process by bringing down this 1 and multiplying, adding those two together, and multiplying, we also see that the remainder is 0 here as well. Now what this tells me is that with 1 as a solution, the factor x minus 1 is a component of the factored result. And the factor x minus 1 is a second component of the result. And what we started off as an x to the 4th power polynomial, because all of these coefficients represented these coefficients to the polynomial, by the time we finished the synthetic division, what was an x to the 4th changed to an x to the 3rd. Now we're dealing with an x squared polynomial. So we've got this function that ends up being equal to two factors, x minus 1, and a third factor, x squared plus 2x minus 8. And as it turns out, this final quadratic factor, and I'm going to report this as a multiplicity of 2, the duplicate factors here. But this factor of x squared plus 2x minus 8 looks to be factorable as well as a standard trinomial. And now we've got a fully factored function that originally was not in any form that we were familiar with factoring before. So most of that was covered in the prep for exam number 5, but I thought I'd just address that one more time here before the final exam. And moving on from here, I just grabbed a copy of a question that we've seen in our review in the past, and we'll just quickly talk about it. You will still have to analyze and determine the behavior of rational functions for this final exam. So one of the first things that I like to do is consider the location of the horizontal asymptotes. And we should recall that that's done by looking at the coefficients, looking at the degrees of the numerator and the denominator. In this case, the degree in the numerator is bigger. Let me say that again. The degree in the numerator is smaller than the degree in the denominator. So therefore, we have a horizontal asymptote at y equals 0. Since we have a horizontal asymptote, we don't have any slanted asymptotes. We might have vertical asymptotes, and we will find those by factoring. I'm going to include this negative sign with the numerator, just so that it's not affecting me when I try to factor the denominator here. In the denominator, when factored, I've got x and x plus 3. And since neither of those can be removed by factoring with a factor in the numerator, they are what we call non-removable discontinuities, and both of them will produce vertical asymptotes. So we've got a vertical asymptote at x equals 0. We also have one at x equals -3. So x equals -3, vertical asymptote, x equals 0, another vertical asymptote. There are no holes in this graph because there were no removable discontinuities. So from here I would consider where our intercepts lie. I like looking for y-intercepts first, and I don't expect to find any here because there is a vertical asymptote at x equals 0. But just for good practice, we'll go through the process here. We're essentially looking for the y result when we substitute 0 in place of x. And clearly, if I make that substitution, 0 in place of x, I end up with an expression that can't be evaluated because I've got -4 divided by 0. So therefore, there is no y-intercept. As far as x-intercepts go, we're setting y equal to 0. And one of the tricks we learned in the past was to set just the numerator equal to 0. But here again, I wouldn't expect to find anything because we have a horizontal asymptote right at this axis. And it is impossible for 0 to equal -4. So we have no x or y intercepts. So we really don't have a whole lot to go with right now, but I could use some test points from here on out in order to determine the shape of the graph. Because I know about these boundaries, so I'm kind of anticipating sections of the graph that might look something like this. And I just don't know which of these graphs or which of these sections would be appropriate. So I'm going to pick an x value somewhere over here to the left of -3. If I can find an x value in this region, then it will represent, or it'll allow me to represent the behavior of the graph in that region. So let's choose an x value equal to -4. So these are test points. When x is equal to -4, I get a y value equal to -4 divided by -4 times -4 plus 3. I'm using the factored form, and I'm just substituting x with -4. This looks like -4 over -4 times -1. And these -4's cancel, and we've got 1 divided by -1, which is -1. So that tells me that when x is equal to -4, we get a y-coordinate of -1. And if this coordinate is part of the graph, then I'm fairly certain that the remainder of the graph has to remain captured by these asymptotes. And I'm happy with that particular sketch. For the middle section, I might pick an x value such as -2 or -1. I'm guessing the math might be a little bit easier if I use -1, so I'm going to try it. So y must be equal to -4 divided by -1 times -1 plus 3. Well, that's going to be -4 divided by -1 times 2, or -4 divided by -2. And -4 divided by -2 is +2. So when x is equal to -1, we get a y-coordinate of 2. And knowing that there are no other x-intercepts, I'm guessing that this graph is going to turn away from the x-axis, and I think it's going to form a shape that exists up here. And then lastly, to identify the final branch, I need to pick an x value somewhere over here to the right of the y-axis. And so I'll use an x value of positive 1 this time. Y is equal to negative 4 over 1 times 1 plus 3, which would be equal to negative 4 divided by 1 times 4. Well, that's easy. Negative 4 divided by 4 is negative 1. So when x is 1, we have a y value of negative 1, and we too see a branch or section of the graph that exists below here, captured by the vertical and horizontal asymptotes. So if you recall, many times the test points are not really necessary. The intercepts are sufficient along with the asymptotes that have been found to find the shape of the graph. However, in this case, with no help from the intercepts whatsoever, I still only needed 3 test points. So there's no need for you to establish many test points or use many test points here. 1 or 2, 3, that's generally sufficient. Additionally, if you choose your test points carefully, or if you're lucky about it, you'll find that you can evaluate those functions without the use of a calculator at all. And that completes the no calculator portion of our test review. In the calculator permitted portion of the test, the questions can be so varied that it doesn't really benefit us a great deal to practice specific styles of questions, but I thought it would be nice for us to look at a few problems and maybe jog our memory with different ideas or techniques that we might use to approach problem solving. Now, we've already talked about the systems of equations in class, so I'm not going to address this one again, but what I would like to remind you is the keyboard shortcut, menu 7.5 and then menu 7.1.1. That's what's going to set up your calculator to be prepared to solve these systems of equations, and here's the solution from class that we had most recently. Menu 7.5, menu 7.1.1 is what produces the reduced row echelon form command and allows you to build an empty or fill out an empty matrix to be executed using the TI calculators. And we did mention also in class, you got to be real careful about appropriate signs and values inside of your function, because one of these is a correct answer to this particular question and one of them is not. While both satisfy the requirements that are established by the equations, only one does so in the real world. Technically, this one does have a small error because the negative symbol was not included. Without that negative symbol, a solution was presented. It just doesn't seem to make sense in the real world. With the negative 3 included, appropriate use of the equation, we do generate solutions that are appropriate for the scenario. So if you have questions on the matrix problems, please let me know. Now, the goal for this calculator permitted portion of the test is to use formulas or techniques that we practiced in an abstract sense to explain real-world problems and to solve real-world or descriptive problems. And we have exactly that right here. Our job is to use a Pythagorean equation to solve for x in the triangle below. And the problem is that x is unknown as part of 2 sides. Now, we should recall that the Pythagorean equation is a squared plus b squared equals c squared. And if we assume that this is side A and this is side B, then the equation could be rewritten as follows: x squared plus x plus 5 squared equals 10 squared. Now, even though we didn't practice problems like this specifically in the class, the thought is that a college algebra student should be able to connect the dots, if you will. You should recognize the Pythagorean equation from prior classes and start making substitutions, and then ultimately figure out a way to solve this problem. One of the biggest mistakes that I see students make is this. They'll report that x plus 5 squared is simply x squared plus 5 squared. And by this point in your mathematical career, you need to know that that is not right. this 2 cannot distribute into both of these terms when these terms are separated by addition signs. You must FOIL x plus 5 with another x plus 5. That's the true meaning of x plus 5 squared. And in the process of FOILing that, you do get x squared, and you do get 5 squared, but you also get some terms in the middle, x times 5 and another 5 times x, or in other words 10x in the center here. Now if we continue to simplify, even if we don't know where we're quite going yet, just by doing some math and simplifying, we might get to a point where you've got an idea on what to do next. So we've got 2x squareds plus 10x's plus 25 equals 100. And by now I hope that you're thinking that all quadratic equations should be set equal to 0 in order to solve. So when we subtract 100, we might have negative 75 on the left-hand side. And we can use a variety of techniques to solve this problem. Since a calculator is permitted on this portion, I'll probably use a graph or the quadratic formula to solve. So as far as a graph goes, we'll jump onto the calculator, create a new page, and this time we'll ask for the graphs page. We'll type the expression 2x squared plus 10x minus 75, and we're on the lookout for 2 points on the x-axis where the graph touches or crosses the x-axis. To find those exact points, because they may not be on nice whole numbers, I'll use the Analyze Graph option to find the 0. And I have to do this twice. The calculator won't tell me both of them simultaneously. So menu 6, number 1. What I'm doing is I'm creating a small window. I'm clicking 2 points on the graph in order to find the locations where the graph touches or crosses the x-axis. It looks like it appears at negative 9.11 and positive 4.11. So x is equal to negative 9.11 and x is equal to positive 4.11. I'm stopping here because the instructions did say to round to the nearest 100th rather than 4 decimals. But I should also recognize that both of these answers are not correct for this particular problem. We can't have an x value of negative 9.11 because I can't have a side length of negative 9.11. So I'm throwing that value out, and I'm claiming that x itself is equal to 4.11. And that's exactly what we've been asked to find, is to solve for x. X is equal to 4.11, and that's the only answer for this particular question. For these last two, they're just clues as to problems you might encounter on the test itself. I don't want to give too much away with these, but this one here, given asymptotes and intercepts, find the equation of a rational function. So essentially, you might be asked something like this: find an equation so that y equals some fraction, say x minus some number or x plus some number, or some form like this. Come up with the rational equation if we're told that there is say a vertical asymptote at x equals 3, and if there's a horizontal asymptote at y equals 2. What would it take to build an equation that has those components? And show me what that would be. Well, in general, and this is pretty vague here, but I'll share this much with you, that if we're looking for a horizontal asymptote that's equal to 2, we've got to remember that our coefficients must reduce to 2, while the exponents themselves have the same exponent. So 2 times x to the first power over 1 times x to the first power would produce a horizontal asymptote at y equals 2. Additionally, we might have a vertical asymptote at x equals 3, so after it's been factored, we must have a 0 in the denominator, such as x minus 3, and that's what would create our vertical asymptote. Now, of course, the question becomes a little bit more complicated if we tell you that there's more than one vertical asymptote. Maybe there's one at x equals negative 3. And the problem with that, of course, is if we add x plus 3 to the denominator, well, now we're talking about an expression that could be written as x squared minus 9, And if we have 2x in the numerator, well, now we have a numerator degree that's smaller than the denominator's degree, and we would no longer have our horizontal asymptote at 2 anymore because that violates the rules. And so then you'd have to consider how to adjust that from there. We could also specify that there's, say, an x-intercept or a y-intercept at a particular location, and you'd want to make sure that the equation that you build meets those criteria as well. So that's, again, a thoughtful problem, something that can't be directly evaluated with just arithmetic. We actually have to think and consider the behavior of the functions. And again, I think those make really good test questions in this particular case. And for this last example, when we're talking about temperature as a polynomial function, we might be given some information that says that a graph that represents the temperature over a given day might appear as follows, where the temperature was 0 at this point, and this point, and this point, and the temperature was below 0 initially. It rose, it fell, and then it rose again. Could you establish the equation that represents this data? Well, if this occurs at 1 and this occurs at 3, and let's say that this occurs at 7, you should be able to determine a polynomial that represents, or that's represented by this graph. We know that the factor at x equals 1, the solution at x equals 1 produces a factor of x minus 1, and x minus 3 for this solution, and then x minus 7 for that one. And we've got to consider, well, what's going to happen if we FOIL this back together. In doing so, we're going to end up with x to the third power plus some other terms minus 21 at the end, because negative 7 times negative 3 times negative 1 produces our constant. And in this particular shape of the graph, I think that would be appropriate, but maybe we are then given some additional information, and we're told that actually the temperature at the beginning of the day was dropping, and then at the end of the day or later in the afternoon it continues to fall. And so we end up with a graph that looks like this. While we would still start with the same factors to produce this shape, because the factors are dependent upon the locations of our x-intercepts, we would then have to consider how would we modify this factored result so that the leading coefficient would represent the direction of this particular graph. And sometimes it might be just as easy as introducing a negative sign here or here. That would not change the x-intercepts at all. But maybe we're then told that actually the temperature started off at 42. The y-intercept was 42, not 21. Well, then we might have to introduce a multiplication or some sort of constant multiplier. What if we had negative 2 times x cubed plus ... negative 21? Well, now we have ourselves, especially after we distribute, negative 2x cubed plus something plus 42 at the end. And this 42 now represents our y-intercept, the negative leading coefficient with an odd degree does correctly account for the direction of our tails. When factored, we still have the factors x minus 1, x minus 3, and x minus 7, so these locations are preserved. And now we've got ourselves a nice polynomial that represents the temperature behavior in this window of time. And here again, I can't give you all examples that you might encounter on the test. We just have to be aware that applying the rudimentary understanding of college algebra is necessary in a variety of contexts. So we're going to see how well you can do that with the calculator permitted portion of the test. If you've got further questions on this or any other parts of your review or other Math Excel questions that you're encountering while getting ready for the final exam, please reach out to me. I'd be happy to help. Thanks for watching.